Unit 3, the line and the jet. You're going to need your booklet, a erasable pen or pencil, and a ruler. Got it? Great. The line and the jet is an introduction to discussion of what are called linear or straight line equations and the jet or exponential equations. And to begin our exploration of that, we have to consider the following. What are known as sequences. A sequence is a series of numbers that follow a specific rule. That rule could be described as a function, f of n, where this is like the formula for finding the numbers in the sequence, and n is which term in the sequence, where each term is the numbers listed. So this is the first term, second term, third term, fourth term, etc. We could technically go on forever and ever or to the nth term. By the way, there also can be called terms, elements, members, etc. This is such an important idea. It shows up in so many different languages. So to begin playing with how weird and interesting and fun sequences can be, we'll say a theoretical Mrs. Rosenblatt gave her students what she thought was a very simple task. Little did she know. What is the next number in the sequence? 2, 4, 6, 8. Did you just say a number? Well, Cody, Allie, and Suri had some other answers. Cody probably said, well, I'm thinking it's a +2 pattern. It continues 10, 12, 13, 16. Allie says, I don't think so. I think it's a repeating pattern. It goes 2, 4, 6, 8, 2, 4, 6, 8. And Suri says, I'm thinking that you're actually talking about the unit digits here, where it's 2, 4, 6, 8, 0, 2, 4, 6, 8, 0. The question is, are these valid responses? And zooming in so you'll be able to see my writing more clearly. The answer is yes. Each response follows a logical rule. And so if we were to explore each response to, let's say the 100th number, in Cody's sequence, we could list that out. We could say, let's see, if it's 2, 4, 6, 8, 10. If I go 100 numbers into that, I'll get 2 times 100 numbers, or 200. Allie thinks it's a repeating number, and so if I think about 100 and I say, okay, 2, 4, 6, 8, 2, 4, 6, 8, it's like a count of 4. And so since a beats of 4 would go evenly into 100, because 100 divided by 4 is a whole number with no remainder, that means that the 100th beat will land on 8. On the other hand, Suri, all I have to do is look at the last digit, and so the last digit is just a 0. What we're going to do is, even though each of these methods are interesting, and each of these in fact create its own type of mathematics, we're specifically going to look at Cody's method right here, because Cody's method is going to lead to our next concept, which is going to be, here we go, arithmetic and geometric sequences. Arithmetic and geometric sequences. Cody's idea of arithmetic, or adding, or a +2 pattern, can be written as a formula in a way that we don't yet have the mathematics to write Allie's or Suri's pattern. What is the expression for the term in terms of n? Remember, n being that, which term in the sequence we're talking about, for the number sequence in Cody's scenario. Now, we can write our formula in 2 ways. We could write something that's called an explicit formula, which if I tell you I want the 100th term, you plug in 100, it gives you the 100th term. Or what's known as a recursive formula. A recursive formula, almost think about it as a ladder, where you use one step to get to the next, to get to the next, and eventually I would get to the 100th term. And the way that would work is I say, okay, my first term, my formula for my first term, says that my first term was 2. Then to get to my next term, so my next term is, let's call it n plus 1. So that's not the term I'm on, but the next one. So the plus 1. So if I'm on the first term, then the next term would be 1 plus 1 or 2. If I'm on the 8th term, then 8 plus 1 would give me 9. Would be take the term I'm on and add 2. If I wanted to create an explicit formula, or one that would power it out right away, I could just say, well, all Cody is doing by saying a plus 2 pattern, 2, 4, 6, 8, 10, 10, 12, 14, 16, it's just times 2. So I could write an explicit formula where I say f of n is just 2 times the number you want to put in. Let's start looking at some more other types of sequences. Jerry has a sequence here that shows what's called powers of 2. Here are the first 6 numbers of his sequence. 1, 2, 4, 8, 16, 32, 64. How would we create an expression for the nth term, both as an explicit formula and a recursive formula? For this one, the explicit formula is actually a little easier because these are powers of 2. So like this is 2 to the 0, this is 2 to the first, 2 squared, 2 to the third, 2 to the fourth, to the 5th, etc. It's pretty straightforward to say that for any term, the formula for the nth term is to the n. Now, by the way, these parentheses, those aren't multiplication, they're just put in the number there. The recursive term on the other says, well, my first term is 1, and to get to my next term, my n plus 1 term, I take the term that I know and multiply it by 2, seeing how each one is twice as large as the one before. So, now let's continue looking at more patterns like this to see if we can establish some habits. Consider the sequence that follows the plus 3 pattern. This is really similar to Cody's rule earlier. 4 plus 3 is 7, plus 3 is 10, plus 3 is 16, is 13, then 16. Write a formula using both what's known as the a to the n notation and the fn notation. Now, we've been using the formula of n notation, so I should probably explain what a to the n notation is. Sometimes a notation is a way of writing things. So mathematicians, some people like to focus on the formula aspect, some people like to focus on the list aspect. So they'll say this is the first term, this is the second term, this is the third term, the fourth term, all the way the nth term. So notice each one is like, this is a part of A, this is the first one in A, this is a part of the sequence A, this is a second term. Each one creates, this notation shows that these letters are all related and where they are in the list, as opposed to this, which kind of more focuses on how you get any number in that list. So coming back to what that looks like, is that if I wanted to focus on using both the notation here and f of n notation, I'd have to think about how I would do a plus 3 pattern. And to do that, I have to decide, do I want to write an explicit formula or a recursive formula? Remember, explicit gives you the term directly. You just plug in for n. Recursive builds. And I have to be honest here, I'm not sure how to write an explicit formula, but I'm pretty sure how to write an implicit formula or a recursive formula. I know the first term of this pattern is 4. And I know to get to the next term, or the n plus 1 term, I take whatever term I'm on, and then add 3. So there's a formula right there. If I were to use the a sub n notation, that would mean the first term is 4. The nth term, well, the n plus 1 term, which is the next one, just see how they mirror each other there, is the term I'm in plus 4. Now, they're about to give us this formula right here, where it says the formula for the nth term is 3 times the number term you're looking for, minus 1, plus 4, generate the same sequence. Why might some people prefer this formula? Notice this is actually an explicit formula. If I go ahead and I set up my t-table, there's my n, there's my f of n. If I put in 0, let's see, I get negative 1. 0 minus 1 is negative 1. Negative 1 times 3 is negative 3 plus 4. That's 1. That's actually not part of my list. So I might not be able to start with 0. I might have to start with 1. So I put in 1. 1 minus 1 is 0. anything times 0 is itself, so 0 plus 4 is 4. I put in 2, 3 plus 4 is 7. Now it's working. I put in 3. That's 2 times 3, 6 plus 4 is 10. And I'm getting the same pattern. Notice as I do that, and then I graph it, so 1 is, let's see, 1 comma 4, 1 comma 4, and then 2 comma 7 would be right here, and then 3 comma 10 right here. Using my handy dandy ruler, I can draw a line, and to follow up the question on the other side, what do I notice about the graph? It forms a line, and what do you notice about the slope of that line? If I look back and I look at the slope of this line, up 3 over 1. It has a slope of 3, just like our plus 3 pattern. So we're going to use the fact that the slope of a linear pattern like this is the same as what's being added in our next lesson. Let's take a look at one last type of pattern. We've talked about multiplication patterns. We've talked about adding patterns. Now let's talk about the square number patterns. If I look at this, this is 1 squared, 4 is 2 squared, 1 squared, 2 squared, 9 is 3 squared, 4 squared, and so on and so forth. The formula for the nth term of the sequence, well, the explicit formula is actually pretty easy. The f to the n is just n squared. Be sure to specify what value of the n your formula starts with. Well, we're starting with 1, so I'm going to say n is going to have to be larger than 1. Using our formula, we're going to find the 50th term. So the formula for 50 is 50 squared, or 2,500. And if we go ahead and we graph these as an ordered pair, you might see some very familiar things start to emerge. Let's see, 3 squared is 9, so that's almost to the 10. 4 squared is 16, so it's halfway between. And then 5 squared is 25, and this is the point where I like to use my ruler. Okay, so that's exactly between 30 and 6 squared is 36, so that would be about right here. 7 squared is 49, so that's just below here. 8 squared is just below the halfway mark. 9 squared is just above 81, and 10 squared is exactly 100. Does this look like a familiar shape? If you remember, this might be something we called a parabola back in Algebra 1. In class tomorrow, you're going to get to discuss both the simple and the complicated sequences. Looking forward. I'll see you there.